Okay, great. All right. Thanks again, and thanks for your patience. So, the title of my talk is What Drives Wildfire Trends in the Western US. And I just want to say up front that we do not have a complete answer for that. These are partial answers for what are driving these trends. And I also want to acknowledge the really great series of graduate students and postdocs that I've had working with me, Amy, Karina, Shu, Makoto Young, Tina, and another Shu. They've been really magnificent in propelling this research. So now I got to figure out how to get, oh, Alyssa has the button. There we go. So recent trends in particulate pollution show some really interesting features. I'm an atmospheric chemist, so I care about particulate pollution, and we often refer to these particles as PM 2.5 because their diameters are less than 2.5 microns in diameter. You can see in the panels on this big plot that for all the regions, Northwest, Northeast, so forth, all the regions show strong decreases in PM 2.5 pollution from about 2000 to 2015 or 16, and this is thanks to the Clean Air Act. But then starting in 2016, PM 2.5 increases in the Northwest, West, and Southwest. Alyssa, if you could push the button, two buttons. Yes. So you see the steep decline, and then you see these very interesting increases in PM 2.5 in the Western regions. And also you see large interannual variability. And a number of really great studies have linked these increases to the influence of wildfire smoke. Next slide. So this recent trend is concerning because many diseases have been linked to exposure to smoke. I'm listing just four here: asthma, lung disease, cardiovascular disease, adverse birth outcomes. And the reason these particles have such diverse effects is that they can penetrate deep into the lungs and cause inflammation. And some of the very tiniest particles can get into the bloodstream. And a lot of work that we've done and many others have shown that wildfire smoke can have both short-term and long-term health impacts. And exposure undoubtedly is worse for people who work outside or who lack air filters in their homes. And you can see some pictures of various workers outside, including some gallant hotshot crew members. Okay, next slide. So why is the wildfire increasing in the Western US? Is it climate change or natural variability? And in our view, understanding the drivers of trends in wildfires and smoke will help guide responses by stakeholders and policymakers. We were some of the first to identify the risk of climate change for smoke PM 2.5. Okay, next slide. So here's mistake number one, outline of talk. I will first be talking about present day trends, and the second part had to do with health, and I've removed that in the interest of time, but I can talk about some of our health studies. And then the final part will be about the future. Again, I've removed a part about what can we do about wildfires and smoke, but I will skip over that again in the interest of time. Okay, next slide. So what drives the current trends in wildfires and smoke? This is a very nice plot put out by some colleagues of mine. And you can see from 1985 to 2020, measures of area burned in forests in the Western US. The gray bars refer to the total area burned and the right-hand axis. And you can see fairly low levels of area burned in the 1980s, except for one big year, but then really ramping up in later years. Again, a lot of interannual variability. And the green and yellow refer to different regions in these forests. So the dark green is wilderness. The kind of yellowy is something called the wildland urban interface, which people in Colorado and California are probably pretty aware of. These are areas where many people live in close proximity to dense vegetation. There are various definitions for that WUI. Everywhere else is in the light green, and the axes for the green and yellow curves are on the left. So what is happening? And I've listed here a number of potential reasons: climate change, wildfire deficit in the West, natural drivers like El Nino, or the population growth in the WUI, just more people around to ignite more fires. Okay, next slide. And so I want to talk a little bit, give background on a couple of the possible reasons. Much of the Western U.S. is experiencing a fire deficit. In the past, many areas experienced frequent but small wildfires, as well as indigenous burning. The indigenous peoples had rituals and practices involving fire. But then during the 20th century, there was massive fire suppression. More people were vacationing in the West, people were living in the West, and this fire suppression, as indicated by Old Smokey the Bear, led to greater accumulation of fuel and more wildfires. So you can see all the fuel accumulating in that middle panel as a example, and then catastrophic fires. The two panels in the upper right show Yosemite Valley in 1892 and then 2011, and you can see the areas being filled in with forests and fuel. Next slide. Next, yeah. Okay, so then with regard to natural variability, charcoal sediments suggest periods of really intense fire activity in past centuries over the West. This is a really wonderful paper that used charcoal records as a proxy for fires. This record starts in 600 AD and goes to 2000. And they use a number of sites in bogs and river or lake sediments. And the gray indicates the noise or the variability, and the red is a kind of smoothed out version of this charcoal record of fire. You see increased fire, some of the, in the translation to Alyssa's laptop, there's some weird things with the numbers, but around 1000 AD, you can see warming due to the medieval climate anomaly and more fires. During the Little Ice Age, in purple, you see a dip in fire activity as suggested by the charcoal. These same researchers also developed a very simple model of fire activity based on temperature proxies and drought area. And the model that they developed depends on climate, obviously, and it works pretty well. You can see that in the dotted line. Next button, please. Yeah. So this simple model tracks pretty well with the red curve, the red observed curve, until you get to about 1900, and then you see this huge discrepancy between what the model would expect given our climate and then the fire that actually occurred. So next button. Yes, so that shows more closely the late 20th century fire deficit. So this panel shows both the natural variability and the deficit. Next slide. So in determining what is driving wildfires in the recent climate, we built on our own and others' past efforts to determine that. those drivers. We started with observed area burn, meteorology, and vegetation. And I think you can click a button right now. Let me see what happens when you click. Oh, yeah. Okay. And then we use machine learning to determine the sensitivity of area burn to meteorology and vegetation. We used Gaussian process regression models as our machine learning base. And then using that sensitivity, and if you could click the next button, please, together with CMIP6, we determined a signal of recent climate change due to greenhouse gases. And using the sensitivity and these signals, we could figure out area burned, and as I'll show you, smoke exposure due to climate change. Next button. The variables that we included in the machine learning models included vapor pressure deficit, temperature, and other moisture variables, as well as vegetation, so year-to-year variability in vegetation. Next slide. Just more details about our approach. We divided the West into ecoregions. For example, here, ecosystem 1 is mainly forested mountains. And you can see it crawls around the West, but we wanted similar ecoregions that would react or respond the same way to fire weather. And the statistical method bypasses some of the complexities of an Earth system model. Alyssa, what time should I stop?
You have a little bit more time.
Okay.
I would say you can go up to 10 more minutes and we should still have
Okay.
enough time for panel.
Okay, great. Okay, next slide. Okay, so I'm going to skip a little bit quickly through the next couple slides, but happy to return to them. Lightning fires, we found that lightning fires accounted for about 2/3 of area burned across the West, but the percentages varied a lot by ecoregion. So you can see in the forested mountains, ecoregion 1, the red lightning fires indicated by the bars, these are all observations, really dominated, whereas in Mediterranean California, ecosystem 2, it was really dominated by human-caused fires, including power lines and other human activities. Okay. I can talk a lot about Mediterranean California. The ecosystems and fire activity is very different there. Okay, next slide. Okay, something really didn't work in the translation. Um, so I'll just give you the the end the the end result was that we found that climate change accounts for 60% of area burned from 1992 to 2020. And we found that our machine learning models really did show good agreement with the observed area burn of 90%. In actually the here I'm just focusing on Northwest US. So these numbers are just for the Northwest US. Hopefully the next slide will show all the ecoregions. Let's go to the next slide. Next slide, next slide. Yeah, here we go. Perfect. Okay, here are all our results in a nutshell. We find that Northwest mountains, as I said, 60%. The percentages really vary by ecosystem. So the most sensitive to climate change are the dry mountain forests in Southwest US. The least sensitive is Mediterranean California. It's very where the ecosystem is heavily populated and most of the fires are due to human activity. There's not a lot of lighting in the Southern California. The orange area with the question marks is an area that we were unable to model successfully. So for now, we're leaving off any kind of calculation or estimate of the driver of climate change. So climate change is having a big effect on the fires in the Western US. And I'm going to skip the next couple slides. Let's go to the next slide. Okay, I'm going to skip, I think, 2 slides. This is about the fire deficit. Again, I'm happy to talk about that. And go to the smoke exposure. What are the implications of climate change for smoke exposure? The left-hand panel shows that smoke accounts for 1/3 of all PM 2.5 averaged over the domain. So that's any smoke, but you can see it's really concentrated. That mean smoke concentration is really concentrated in California, Oregon, Idaho, a little bit in Colorado. The two right-hand panels are very interesting. They show how much of total PM 2.5 consists, this is total PM 2.5, consists of smoke due to climate change and smoke due to natural drivers. And you can see that in California, Colorado a bit, Idaho, Oregon, really large percentages, greater than 50%, are due to climate change. So what that says is that climate change is really ramping up the burden of particulate matter in the Western US and having an effect on health, human health. The effects of natural drivers are more widespread, but smaller amounts. Okay, let's go to the next slide. And this should be section 2. Again, there's a little bit of the letters don't quite line up as they do in my letters and numbers don't quite line up in WebEx. Okay, this should be section 2. How will wildfires change in the Western US as global climate changes? So we know temperatures will undoubtedly rise, but variables related to moisture will also change. And I'm highlighting 2 variables. One is vapor pressure deficit. That's a measure of how dry the air is, often used as a proxy for something called atmospheric water demand and how dry the land surface is. And then there's soil moisture, a direct measure of how dry the land surface is. So a tree or a grass sees both VPD and soil moisture. The forest litter, which doesn't show up well in this graphic, also sees both VPD and soil moisture. Both soil moisture and VPD are correlated with historical area burned over Western forests. This is from 1984 to 2014. Each dot represents a different year. As VPD goes up, that means more dryness and greater area burned. And as soil moisture goes down, again, more area burned. So people want to know what's going to happen in the future. And many, many researchers in my community like VPD. It's easily calculated from climate models. It's easy to understand, and soil moisture is sort of a different variable. And which variable is used has become very controversial in the last couple of months. Let's go to the next slide. We first look at how do these moisture variables change in the future atmosphere. And we see plotted against projected change in global mean temperature rather than in year. So this is the change from pre-industrial conditions. So what's going to happen in the future? And present day is way over on the right-hand side of this plot. Then we see how the CMIP6 models estimate changes in VPD, vapor pressure deficit, and soil moisture. Both indicate a trend toward drier conditions. But VPD is going up more rapidly than soil moisture is going down. And again, VPD is very easy to calculate from measurements or from model results from CMIP6. And so people have preferred VPD. So we did, as a first test, very, very simple models. We put together a model using only VPD to project wildfire area burned in the future. These are regression models based on present day. And we used soil moisture, and we only looked at forests in the Western US. Next slide. So this plot shows how these very simple models project area burned in forests in the West as the climate warms. The present day is in that purple circle, and then you can see how the area burn trends change with increasing global mean temperatures. At 3 degrees Celsius increase, we see an increase in present day area burned by a factor of 16 in the VPD trend. In the soil moisture trend, we just see a tripling of area burned. In the present day, both models, these simple models, roughly agree, but then there's this divergence. We also see a similar divergence with more complex wildfire metrics that are not yet ready for public consumption, and other people have tried, another paper did try more complex metrics. And our view is that, in fact, VPD, while it seems to work in the present day, is actually a poor measure of atmospheric water demand by plants. And the reason is that the plants have these feedbacks when it gets drier. Their pores will, their stomata will start to close. They're not so responsive to VPD. They are responsive to soil moisture. And there are feedbacks between VPD, plants, and soil moisture that are not captured by these statistical models that have become very popular with the fire community. So we argue that VPD projections are not so reliable. And the implication that we state is that wildfires will increase with warming, but by much less than that reported in some papers. Next slide. And just very briefly, our results are more in line with those from complex dynamic vegetation models, which really consider the whole ecosystem, the soil moisture and the fire activity from nearly first principles. This is from the CLM model with a similar 3 degrees warming, and basically that model shows a 2 to 3 increase in area burned across much of the Western US in this scenario, more in line with that from the soil moisture model. So our work is in review. This has not been resolved yet, but stay tuned. Next slide. And I think this should be the end, right? This is the end. Okay, so just basically smoky air is a major consequence of climate change in the Western US. And I want to thank and acknowledge the efforts, particularly at the 3 gentlemen on the bottom row, Jed Kaplan, Kagan McCall, and Yu Chen, who have really helped inform this research. It's very interdisciplinary, and we value their input. Okay, that's it.
Yeah, thank you, Loretta. That was very interesting and thought-provoking. I have many questions, but I guess I'll start with the soil moisture. So can you talk a little bit about The source, well, okay, I guess starting from the theory, what depth of soil moisture are you using? And is there any theory about what depth of soil moisture we should be using to relate to wildfire? Because I know there's a divergence between expectations of how surface soil moisture and root zone soil moisture will change in the future. And then if you could just talk a little bit about where the soil moisture data or estimates or model in those graphs was coming from.
Okay, good question. The soil moisture is in the surface, but I think that going forward, we want to consider deeper soil moisture as well. This is new work. And would you recommend using the deeper soil moisture? Is that your view?
No, this is a legitimate question. I mainly work on
Okay,
agriculture, and so I know
okay.
looking at forests and forest wildfires is a different vegetative landscape, and so I don't have an answer in mind. I was interested.
Yeah, okay.
Okay, next question is Sanjeev.
Yeah, thank you for this great presentation. I think my question, Weston already asked me. Yeah, I since I work on those areas, I do recommend using the deeper layer, at least root zone, maybe around one up to 1 meter depth.
Okay.
Not not full depth because yeah, there can be so. Um, mm, uh, my question then I can ask the next question. Some of the ILA's work has shown that VPD projections are not very good in CMAP class of model, particularly in the Western US. Like if you see the observation, then yeah, VPD are not increasing. So have you kind of considered those work, and what is implication of those work on your
I have not seen that work, and I would be very pleased if you could send me some of those reports. So you're saying that the VPD from CMIP6 is not reliable?
Yes.
Okay, that's really interesting. Are the so what about so in our first project looking at the drivers of climate change, we did use VPD in the present day. Um, and we looked at departures rather than the absolute amount from CMIP6 because of certain biases in temperature and rainfall, for example. We just looked at the departures from a mean. Um, but that's really interesting. I would be pleased if you could send me something on that.
Thank you.
All right, I'll say we have time for one more question and then we need to do some panel business. So go ahead, Val.
Hi, Loretta. Nice presentation. So I have probably a follow-up questions. You found that climate change can contribute to 30 to 80% of the area burned in Western US.
In
So
some regions.
in some regions, if I remember correctly, many CMIP6 model cannot capture from the historic simulation cannot capture this moisture and precipitation change in the Western US. If you look at the same period, model may project may simulate increased precipitation, but observation we see is like a decreased precipitation. So I'm curious, how do you what is your QCL methodology? How do you get this attribution from, yeah.
So this is for the work looking at present day trends. Is that correct?
Yeah.
Okay.
During present day, you probably need some kind of model to.
Yeah. So for the present day, we relied, you're absolutely right, on CMIP6 output to determine the impact of climate change. And we used the two sets of models, the models that were all naturally driven and the set driven by increasing greenhouse gases. We use an ensemble of models, And as I recall, precipitation was not very helpful in our models, in that many of the CMIP6 models showed no trends. They were much more, our work was much more reliant on temperature. So
Soil moisture is related to precipitation, right?
soil moisture is driven by, in large part, by radiation, net radiation. So this is work that my colleague Kagan McCall put together, and yes, precipitation plays a role, but also just the latent heat, sensible heat, solar radiation. But you're right, there are certainly uncertainties in the precipitation from CMIP6, and the spaghetti plots showing all the models and how they changed over that time period were, I mean, the spread was enormous. And we acknowledge that in our paper. That's, we know that. So,
Okay, thank you.
yeah.